Okay, hello everyone. My name is Thomas Ressler Antal. I'm a junior PhD student at the Computer Vision and Learning Group at the LMU Munich, which is supervised by Björn Ommer. And today I would like to talk a bit about how to learn disentangled motion representations from videos and how to utilize them for the task of open world motion transfer. So first of all, what is motion transfer? You always start with the source video where you would like to extract the motion from. And importantly, this motion should be as disentangled as possible from any static information from the video, such as the appearance or the structure of an object or just generally the content, because what you're interested in is some form of representation of the temporal dynamics of the video. The next step then, of course, is to apply it to some new content. This can be in different forms. This usually is in form of a text prompt or as in this case, a static image. And what this does is, what you essentially want is to marry these two counterparts now together. You lost your static information from your motion, from your source video. You got some new static information from your new content. And then, of course, eventually, what you want to have in the end is a somewhat convincing video that you have to render in the end. And the important part here is how this motion is being represented. And this is also what our work tries to, or where our work tries to accomplish some new paradigm. Most other work that is tackling motion transfer usually represented with some structural cues and some handcrafted representation that is usually based on the structure of an input video. This can be either explicitly, for example, in the form of some key points, if you think about a motion capture suit in Hollywood studios, or facial landmarks if you are only interested in faces. Or it can also be implicitly, for example, if you have an existing video model and maybe a diffusion video generation model, or maybe even a video representation model, you could also find some metric how to combine or aggregate the temporal information to construct essentially a motion representation out of it. But this comes with a few problems. So, because for existing work, the motion representation is so inherently fused together with the structure of the video, there is usually like a trade-off between the motion fidelity and the adherence to the target prompt, essentially. These are some baselines, luckily not our model, where you have, for example, in the left you can see that the model fails to transfer the camera motion of the input video. It can adhere to the prompt faithfully, which is here a text prompt, but it just doesn't understand what it should do with the camera motion. Here in the second column, there's me waving around with my arms. But here the model or the baseline model faithfully transfers the motion of me, but fails to actually adhere to the prompt that is given with the text prompt. And then in the third column, sometimes the entire content just starts to bleed through. And because of this, or to tackle the problem, we introduced Tismo. And basically, what we do is we introduce an abstract motion space, or a motion space that is not based on like handcrafted features, but it is abstract, maybe similar to what we already have for a long time in the image space, for example, clip or dino features, which hopefully tackles the problem of this trade-off. And what we do is we introduce like a motion extractor that takes a source video as an input and then extracts a stream of these abstract motion embeddings. And then for the task of motion transfer, what we do is we adapt a video model. So we fine-tune an existing video model, give it like the target content where we want to attach the motion to, alongside a stream of motion embeddings, in order to transfer the motion onto the new target. And with this, we are actually disentangled from the appearance and structure and the pose and even the object category, as you can see in this case, where other baseline models struggle. Here you can also see a bit the capabilities in a nutshell. We achieve high motion fidelity usually also for tasks where the object category is completely different, and without losing any adherence to the source prompt, as you can see on the right. And in the middle there is even a more extreme case. There's only a hand and the target is a monster, and there is no content bleeding at all. So to go in a bit more detail about the method, for the motion encoding part, what we have is the input video at the top, and the motion extractor at the bottom. And the first thing we do is we apply some geometric and photometric augmentation to the video, and then patchify it and input it to the motion extractor alongside a learnable query embedding. And the output then is a stream of motion embeddings, where you have one global motion embedding for each frame of your video. Actually, except for the last one, so this is a bit of a mistake in the slide, because of course you can know the motion of the last frame because you don't have your next target frame. What we then do with these motion embeddings, as a second base module, we have a frame generator, which receives each video image at time t, xt, alongside the motion token or the motion representation that was just being extracted of the motion encoder. And it is tasked to predict some frame in the future, essentially. And the frame generator is a flow matching method, because flow matching is the new kid on the block, of course. And this gives the entire loss to both the frame generator and the motion extractor, essentially. We also do not only predict one step into the future, but we sample the delta time, essentially, to make the motion embeddings encode a longer temporal history or temporal horizon, essentially, and make them a bit more semantic, because that is also, of course, our goal, to make them more semantic. And what this introduces essentially is like the generator receives two different streams, one content stream and one motion stream. And the motion stream acts as a bottleneck to the model. So the model is inherently incentivized to use the motion space as efficiently as possible. And what it does then is that it takes all the static information from the source frame that is being provided and only essentially encodes an abstract representation of the delta in the motion embeddings. Once this setup is trained, we could already use the frame generator and the motion extractor to for an autoregressive video generation or in motion transfer, where you simply start with a start image and motion embedding of some source video that you could just extract, and then you could autoregressively roll out and generate your new frames on the fly. However, it works, but the quality is often not comparable to like state-of-the-art video models, because our frame generator has of course fewer parameters than like 2 billion or 5 billion parameter models. And that's why in practice we actually utilize a pre-trained and larger scale video model for that. So here is a video model with frozen intermediate layers, and then we fine-tune it using our motion embeddings with some LoRa layers. So the rest is still frozen, and then we fine-tune some lighter weight LoRa layers for that. So first we get some motion embeddings from a source video, and then we apply some mapping network, which is a 2 or 3 layer MLP, so nothing special. And then we essentially route each motion embedding to the particular tokens that correspond to the temporal time step of these motion embeddings within the video model, essentially. And this is a very, because we use LoRa's, this is a very efficient method. It also converges quite quickly. We need like 10 to 20K iterations, and then this fine-tuning already works. And here are some intermediate results with that, or some basic results. As you can see, so to the left you can see the source video, and the middle and the right column are generated videos. The video model that we use is CogVideo-X, which is a 5 billion parameter model. And yeah, of course, the interesting part is that the pose and the angle, the camera angle and the pose, the appearance and everything is quite different from the source and the target. But because we are working in an abstract motion space, this isn't really a problem. We don't have any structural key points or whatever that would need them to align perfectly structurally, but instead we are acting in a more semantic, more intelligent latent space. Here are some other examples. As you can see, there's targets are from completely different classes. Again, for example, the head of the dog and the head of the rhino are starting from completely different angles, but it still works. Here is some, yeah, I put too much examples in maybe. Here you can also see that it actually also works for camera motion transfer, which could be quite interesting for maybe re-rendering specific scenes from, or re-hallucinating specific scenes from different angles. Some cuter results maybe. This MoCat. And yeah, I quickly skim over the results. And yeah, we also, of course, ablated this quantitatively. So there are different baselines, and we analyzed it in different, from different angles. The first one is motion fidelity, where we basically measure how aligned the target motion is to the ground truth, or how it should be. Then the prompt adherence, where we basically measure the clip similarity between the generated target frames and the target frame that was initially given. Temporal consistency, which is probably more of a video model metric, but still it doesn't destroy that. And then in the end, the driving video similarity, which should be pretty low, because you do not want to have any content bleeding, as I said, from the source to the target. And then we also had some human evaluation, because this is always necessary in this field, unfortunately. And yeah, then some more analytic or the downstream analysis on the actual motion space that we learned. Because our hypothesis, of course, is that it must be disentangled from the appearance. And for that, we implemented an experiment where we had a data set called IARD, which has, I think, 5 different actors performing 5 different actions. And then we compared our motion embedding space against other video representation learning methods, specifically VJEPA and video MAE, in a retrieval setting. And the result is exactly what we want, basically. Our motion representations retrieve the action of a person with a high accuracy, but the identity of a person with a very low accuracy. So basically, our motion representations retrieve the content just a little bit higher than by random chance, which is exactly what we want. The second test which we did is to check whether our motion representation space is actually semantic or it is still pretty low level. And we tested this on a similar setup, again against default video representation learning methods, on some data set, ARID, gesture, SSV2, and IARD. We chose these data set because they are quite motion heavy and not appearance heavy. This is, by the way, also a big problem currently for evaluating video representations. Most of the data sets are very heavily steered towards appearance. Yeah, but here we can also see our Dismo beats the other baselines, which is a nice hint that the motion space that we learn is actually also quite semantic. So as a recap, what do we have now? We introduced Dismo that learns an abstract motion representation space. We used it for motion transfer. So basically, this allows us to reimagine the motion from one source video or one source object on new target objects, or how they would move if they were moving their arm, which is, of course, you could think of how it could be useful in, for example, CGI Hollywood movies, where currently the animators still have to manually animate frame by frame. But more importantly, maybe, is the more general fact that these motion embeddings actually act as a counterpart to self-supervised image and video representations that were there for a long time now already, and people are still focusing heavily on that. If you imagine video MAE, video VJEPA, or Dino even, generally image and video representations are heavily used. They are also being used in metrics, and we hope that Dismo, or the motion space that is being learned using the Dismo paradigm, could be a first step towards similarly semantic and abstract representations of motion in a video. Possible other downstream tasks that could be thought of are what I just said. Video metrics and video datasets are often very appearance-based, appearance-heavy. And for example, for the prompt adherence metric that I've talked about before, for example, also a clip representation space was used to measure how similar the content is. Similar metrics could also be used for different motions of a video with these abstract representation spaces. Another thing could be also, if you think in a motion retrieval setting, maybe you would like to retrieve similar videos, but whose motion or whose actors are performing a similar motion, or not necessarily the actors look similar. So yeah, and some open problems, what there still are, of course, is like Gizmo isn't perfect. There is still some appearance leakage going on, especially in scenarios where the content suddenly changes from one frame to another. The extreme case are scene cuts. And of course, there the model has no other way of but to somehow encode the entirely new content of the new frame into the motion embedding. That being said, another problem is also maybe that the prediction is still happening in RGB space, and which is of course inherently appearance dependent. And there may be also better prediction targets, for example, optical flow or even longer tracks, video tracks, using tracking mechanisms which got pretty strong over the recent years. One other big factor, and that's why I will also quickly show some recent work of our lab in that direction, is that these Gizmo motion representations are of course global. So for each frame, one motion representation represents the entire frame, but the real world is of course compositional. In a single scene, there could be many different objects, many different people, for example, and these people also, of course, consist of different subparts, or maybe you would only be interested in the head of the person to the left, or of the arm to the person on the right, and so on. So the real world is complex and hierarchical. And for that, unfortunately, so everything from now on, because I'm a junior PhD, this is my only paper, this is everything what I will say now is unfinished work, so I unfortunately can't go into detail. But we are also working on localizing these motion representations. So you can imagine maybe you have like a target image with different animals, like you can see here, and you would like to use the motion of this video and attach it to that animal, and so on. So this could be a much more powerful paradigm. Some first examples you can see here. So to the left is the source input video, and the object of interest is marked by a blue outline, and the target object that we want to apply it to in the middle row is also marked, is outlined by blue. And you can see that the right object is actually doing the motion. Here are some other examples. It's maybe a weird example. And of course, also the model sometimes does some weird stuff. But the motion is correct. And yeah, in this case, it's even two different objects applied to two different video motions applied to the same scene. And finally, another possible task that could be used beyond motion transfer is maybe this motion space that we now learned could be actually useful for planning, maybe for robotic planning. I'm not a robotics guy, but so I'm not sure if this is groundbreaking or not. But essentially what the goal might be is, hey, why don't we plan in a more compact and semantic representation space and only render out the action, and then map it to actions, and then only render out the actions in the end. And the first results work kind of okay. Of course, not always, but it is possible to plan in that space. Yeah, finally, feel free to visit our project page. Here is a QR code, but you can also just put Gizmo in Google if you want to. The code is very straightforward, so if you are interested in extracting some motion representations, it's really easy. Given some video, in this case a dummy video, you can just load our motion extractor with Torch Hub, and then in a single function call just extract motion embeddings. And this forward sliding method is actually a sliding window method, so you can put in arbitrary length videos. And for motion transfer as well, you need a driving video, a target image, and optionally a text prompt. But because cogvideo X is inherently a text-to-video model, I would advise also using a text prompt for better quality. And you can simply load cogvideo X and then call the sample function provided to transfer motion. That was it. Thank you.